right there. But, a number of other things you can do with this method. Here's, you look at a large number of performance problems. Take an energy balance. In this equation, what we have is the equation between fuel energy used and the aircraft's energy state, okay? You know, this is the mechanical efficiency of a power plant. This is the heating content of the fuel. This is the fuel flow. Of course, the airplane weight is changing, so its energy state is changing as the reverse of the fuel flow, okay? And this is the drag and its velocity as it changes with time. So we can use that equation for a whole number of things. If we differentiate our simple energy term here, it looks something like that, top one. And of course, the change in weight is the fuel flow, how many pounds per hour kind of thing. And if we substitute that into the equation, why we have that previous equation, we have something like this. And of course, E sub s dt, we know as we call that P sub s. And so we have an equation which combines both engine performance, this part, with airplane performance. And we can use that to do a bunch of things like range. You know, there's the range, the yard equals the airspeed over time. Change in range is the airspeed over time. And we can plug that into that equation, and okay, here becomes our range equation. So, whole number of things we can do. Now to solve this E sub s term requires minimizing or maximizing a given variable, and of course to do that we have an equation that looks something like that, an integral equation where we have P sub s change with time. And to solve those in the classical sense requires using the calculus of variations, but this isn't a math course, so we're not going to do that. Turns out there's a simpler method. And in the altitude velocity plane, those equations are satisfied when the contours of constant specific energy are tangent to the contours of constant specific power. And when we connect those points, we have the minimum time path to a given energy level, which we talked about a while ago. Normally, you know, we climb an airplane between these top points. That's, you know, those top points are best rated climb speed. But if we want to get to a given energy level, let's say a certain altitude and airspeed, then we use where these lines are tangent with these lines. And notice that is an increasing airspeed as you go to altitude. And of course, I already talked a little bit about this, but here's the minimum time path for that guy, for that interceptor who wants to get to a given speed in a supersonic.
I'm just curious how it translated into rate of descent in order to get that. I mean, it's not a constant Mach number and it's not a constant altitude. So
No,
what do they pitch for when they were trying to do that?
It is changing. Well, here, this, you know, you get up close and then you descend at whatever that constant energy state is. That's the.
I mean, that's got to translate into something on the indicators for the pilot and rate of descent. But what is that?
Right. Well, I think in a lot of cases, they've got that programmed into the HUD,
Oh, yeah.
okay? So that he can see what's going on.
You just try to keep them on as fast as you can.
You can do the same thing with this, with a whole bunch of things. A minimum fuel decline, maybe you wanted not to burn so much gas getting up there. Well, then you would do it, you'd plot contours of piece of S over fuel flow, okay? And then put the constant energy lines tangent to those. Max range, well, you plot drag, okay, here's a minimum fuel path, okay? These values are piece of S over fuel flow, constant values of that. Notice that
Follows a similar path.
it follows a similar kind of path. And here's a guy, here, you flamed out way up high. Well, here's how you get the maximum range glide to, make it to someplace you can land. So lots of ways you can use this. Okay, all right, out of time, questions?